Good evening, everyone. It's our pleasure to present to you Professor Kang. Is going to talk about fixing the NLP pipeline with humans and data. He received his PhD from Carnegie Mellon University, and he has spent some time at some very prestigious institutions like Berkeley, Facebook, AI2, and others. So, DK, the podium is yours.
Okay, thanks for the introduction, Nikos. All right, so I'm Dongyeop or DK. So in today's talk, I'm going to talk about a couple of our recent projects that our group has been working over the summer. And many of them are actually under review. So yeah, please don't distribute it yet. And also, I will give you one summary of my talk today. So basically, I'm trying to fix the current NLP pipeline with by involving humans and the data into the loop. So that's the one summary, one line summary of the whole talk. Okay, and please feel free to interrupt in the middle of the talk if you have any questions, or if you put your questions in the Zoom chat. I'm gonna check them out in a regular basis during the talk. Okay. So first of all, most of the work that I'm going to present today are conducted through the collaboration with the students and researchers from various institutions. And many of my slides are actually borrowed from the authors of the papers and other researchers, okay? Great, so as you know, I'm gonna talk about a typical machine learning pipeline. And even like NLP people just follow this machine learning pipeline to train the model and then evaluate the model and then deploy it to the real world. So for instance, we collect data sets, and then the data set is annotated by multiple annotators. So you often use the crowdsourcing to collect the data sets. And then once we collect data set by multiple annotators, we measure the quality by checking the annotators' agreements. So if many people agree that, oh, this is positive sentiment, this is dog, this is cat, then we say, oh, there is a consensus among the annotators. So yes, it's correct label. And then once we collect the data set, we split the data set into train set and test sets, and then train this like this fancy neural nets or deep learning models on the train sets. And then we evaluate the system on the held out test sets. And if the model outputs, if the model makes some outputs that requires some human judgment, like a text, generated text or generated speech, then we also invite human evaluators to determine how coherent or fluent the text is. So there should be some human evaluation as well. Thanks to deep learning, we have achieved near human-like or more than human performance on many NLP tasks, and we are like celebrating like, oh, we made a huge impact on the NLP community. We solved the problem and so on. Is that true? So when you deploy this kind of NLP system that achieves almost like a human-like performance, and if you deploy it to the real world, you will see a lot of problems. And also even like the real world system that you're using in your daily life, have you seen some advanced NLP systems? Maybe not. Maybe you see like maybe like Amazon Alexa, Google Assistant, maybe email supporting system, and so on, right? But not that much like academic people actually working on. Why? And also you may heard about like Amazon Alexa, their backend system is entirely like a rule-based, not just a pure like end-to-end neural system, but many of the rules are involved to control this output from the neural system. And there are many like a human control not to produce any like wrong decisions at the end, right? Why? So what's the gap between this academic NLP performance and more real world deployments of NLP systems, and how they're different, and what's the gap between them? So here are some examples where this academic NLP system or the current state-of-the-art NLP system fail in practice? Let's start from this example first. So this is a typical question answering system that many NLP people use. So the task is, given a passage like this, like Peyton Manning becomes the first quarterback over to lead two different teams to multiple Super Bowls, blah, 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 and so on. And then the question is, what is the name of the quarterback who was 38 in Super Bowl, blah, blah, blah. So can you guess what the answer is? Okay, the answer is John Elway. If you take a few minutes to read the passage, you will easily find it, okay? And the system also makes a correct prediction. How? Because there are a bunch of this sort of like a question and answer and passage pairs in the training data sets. And neural models or deep learning models are trained on a bunch of this kind of labeled data set. This is how it works. I will give you a really interesting phenomenon then. If I add a random, not random, but somehow relevant sentence at the end of the passage like this, oops, wait. Okay, so there's the prediction after adding the sentence shouldn't be coming up before I click the button anyway. And then if you add this random sentence at the end of the paragraph, the system makes some weird prediction, which is the answer is javelin. So you can see that how these kind of neural systems are easy to break it down by adding some simple adversarial examples at the end, or maybe simply change one word to other one. And then this entire system makes a really weird predictions. So we call it robustness. And these neural systems are not trained on learning the task. To answer the question here, what kinds of learning procedure you need? You probably need some reasoning. You probably need some lexical pattern matching between question and passages and so on. But these systems are just learning simple pattern matching patterns, but not reasoning or the more like a thought, human thought process. Okay, I will give you another example. So this is another task called textual entailment classification. The task is basically give you two sentences. One is premise and the other one is hypothesis sentence. And then the model is supposed to predict whether these two sentence pairs are entailing each other or contradicting each other or neutral. So can you guess the first one? Entail, contradicts, neutral, which one? It's entailing, of course, right? What about the second one? An older and younger man smiling. Two men are smiling and laughing at the cats playing on the floor. It's definitely neutral. What about the third one? A man inspects the uniform of a figure in some East Asian country. The man is sleeping. So it's contradicting, right? So these are like a typical NLP task. And then, as I said, these kind of pairs, like premise, hypothesis, and their annotated label, like a contradict, neutral. We collect a bunch of this kind of data set and we feed it to the big neural model, and then we train it. And then we achieve, not we, but the community achieved near human performance. So it's better than actually human. Okay, I have a question. So yeah, go ahead.
So could you just go over briefly again the entailment neutral contradiction? So it's like relating the premise and hypothesis. Is that
exactly? Yeah.
So like if the hypothesis has something to do with the premise, then it's entailment, or?
So if the hypothesis text includes some information that entails from the premise, it means entail.
Okay. All right. Thank you.
Yeah. Any other question? Okay, let me move on. But and then we take the state-of-the-art textual entailment system, and then we did some little trick. So now I give the same premise and hypothesis sentence, but now I just change the verb of the premise to the negation. And then it turns out the system still think this is entailing sentence. How about ordering? So I take the same sentence again, but now I flip the subject and the verb in the sentence, which is obviously a contradiction, but the system says it entails. So it's so easy to fool this kind of neural machine system, even though they achieve the human level performance on their test sets. But in the wild, if you try different kinds of linguistic variation or different kinds of some adversarial examples, it's so easy to fool them. And then why this happens? So this is one paper that actually looking into the data collection parts of as a reason of this kind of brittleness of the neural model. So this is how they collect the data set. So they provide a premise sentence like this, and then annotators are supposed to generate the sentence that entails the premise, sentence that neutral to premise, sentence that contradicts to the premise. And then they do over and over again, and then they collect the data sets. So this is how they collect the data set, training data set, okay? But the thing is, they found that there is some common strategy of generating some entailed hypotheses by removing some gender or by removing some number information, but still make them to be entailing the premise sentence. For neutral hypothesis generation, they often like adding some purpose clause and so on. For contradicting sentences, they just put some negation that generate the contradictions. So basically the system is learning this kind of frequent artifacts imposed by the user on the annotators, not about learning the task, which is the reasoning between the two sentences. So if you train the system, so these and then this annotation artifacts in the training data set makes your system to be biased to only learn this sort of like a frequent patterns that people impose it in the training data set, not learning the task. So the funny thing is, if you simply train your system, not just looking at the two premise and hypothesis sentence, but only looking at the premise or only looking at the entailment, the system achieves almost like a comparable performance, which is funny, right? So it's basically learning this kind of biases from the training data set. So how can we remove these annotation artifacts or other types of data set bias, and then focus on collecting more informative and high quality data sets? So that's the question. And this is the last example. So this is a task called the sentiment classification. So given a sentence like this, you're supposed to predict this is positive sentiment, this is negative sentiment, this is neutral, which is pretty easy, right? And then we achieve almost like a over 90% of the accuracy for this task on the benchmark set. But then people was curious to see whether this is true in the wild, in the real world cases. So they make a simple testing scripts, like software engineering people use their testing scripts for validating their programs. They make this simple testing scripts, and then the first script is about using this template. So they make template like I negation verb the thing, and then they retrieve all the sentences that matches with this templates in unlabeled data sets. And it turns out, and then of course, the expected label from this retrieved sentences should be negative sentiments, right? But it turns out 76% of them turn to be like predicted to be like positive or not negative, which is surprising, right? Also, when you look at this, so now they change some named entities. Some named entities in the sentence to another alternative. So for instance, in the first sentence, it's probably tweets. So thank you, we got on a different flight to Chicago. This is the original sentence. And the prediction about the original sentence is positive sentiments, right? But then if you change the Chicago to Dallas, the system changed its label prediction, like from positive to neutral. If you change the Brazil in the second sentence to Turkey, it also flipped the label. And then 20% of cases happen with the simple heuristic rules. So this is so surprising, and this is one of the best paper awarded in our NLP conference conference. And people got shocked, like how this kind of neural or deep learning systems are brittle to break it down, and what's the problem, how we can fix it. And then people think about the robustness and generalizability of this neural systems and so on. Okay, then the even worse thing is, we like to fix it, but we use the neural nets. So it's, as you know, like this is neural, like a black box model. There's no way to control the system's outputs, no way to interpret why this output comes from this neural system, right? So this transparency and explainability is the biggest issue in our field as well. And many people are actually working on. So let's go back to, then my question is how we can fix these problems. And my main claim today is we can fix this with help from humans and data. And then let's go back to this machine learning pipeline. And the first part of the talk, I'm gonna explain about like how we can make model and humans to interact each other, and then interpret the model's outputs by humans' perception, vice versa, or make them to collaboratively fix the errors and so on. So it's basically human and machine in the loop system. So I will give you a couple of recent works in this direction first. So first work is about interpreting humans' perception in the linguistic styles. So before that, what do I mean by style here? So maybe people from non-NLP area have no idea what do I mean by style. So here's an example, an interesting study conducted in South Korea. So they collected all different kinds of messages that people at companies responding to their boss, their supervisor. So these are, sorry, it's written in Korean, but basically, so this is English translation of each message. But and I know like it's not a real English, but you can just think about it as just a direct translation from Korean to English. And then it's basically meaning like, oh yeah, yep, or yep, or yes, haha, yeah, or yes, that, yes, sir, and so on. And then what they did is they project this different variation of yeses into 2 dimensions. One dimension is how they're polite or impolite, which is y-axis here. The x-axis here is how active or passive they are. And then they do some user study to see that, oh, hey, you better to use yes, that, or yep, colon, to your boss. Because they sound very passive and impolite. You better not to use this, sorry. And then you better, and then like using like a yep or yeah or yep, haha, make your communication with your boss more smooth. And also maybe yes, sir, exclamation mark, as Nico said before our talk started, would be the best choice if you want to show your respect or loyalty to your boss. So of course, these findings highly depend on cultural or pragmatic differences across countries, right? So this might be true in South Korea because we often use more polite or respectful languages to the elder or supervisor, but it's not going to be true in US or other Western countries, right? But the main message here is that these all like messages are meaning yes, right? They have the same semantic meaning, yes, but their stylistic meaning is totally different, and that stylistic meaning can drive totally different social relationships in their communication. So this is why style is important. And maybe when you develop your robots, you don't like to make the robot always saying like, hey, implied or very rude sentences, right? So you like to somehow control their stylistic features of the utterance. So this is why we have to think about the stylistic features are important towards the human-like conversation or dialogue systems. Anyway, so this is a general introduction about the style. And then in one of my PhD work, we collected different types of styles and their benchmark data sets, and then see how they're correlated, or whether we can actually predict the style of the text, whether we can generate stylistic text, like generate this text to be more polite, generate this text to be more humorous, and so on. So there's a bunch of work I have done during my PhD, but I'm not go over that. I will give you the brief introduction about these 4 groups, and then I will jump into the human perception part, okay? So personal group is about your speaker's style. So if you're a person of age maybe 20 to like a 30, or if you're female, if you have maybe PhD level education, maybe there might be some stereotypical language that certain group of people use, right? This is called the personal group. Interpersonal group is not about the speaker, but about the listener. So if you talk to your advisor, or maybe if you talk to your fiance or your friends, your all wording might be different. Your all style, lexical choices of your utterance would be different. So maybe the formality level will be different, politeness level will be different. So this is all about like an interpersonal group. And then in the middle, like there's an affective group. So it's about like sharing the affective status between the speaker and the listener. So whether I like to make more offensive text, or whether I like to make text more romantic or more emotional or more sentiments. And then in the middle, a figurative group is more high level concepts, which is basically making the text or communication more humorous or sarcastic or metaphor. So each of these style types are is heavily studied in NLP, and then cross style or combining different styles all together. There are some many like a cross style research also has been conducted these days as well. So, but then that's not our focus today. So let's jump into the next part. So now we ask how humans perceive these kind of styles in their communication. So here's an example. So the sentence like human written sentence like, I will understand if you decline, but would very much like you to accept. May I nominate you? So what do you think? So do you think this is polite? Do you think this is positive, joyful, offensive? So we ask these questions to human, and human think, hey, this is polite and positive. And there's a little bit of like joyfulness as well, but it's obviously not offensive. Okay. And then multiple people also agreed about these decisions as well. Then we go one step closer. So let's focus on the politeness first, okay? And then we ask, hey, why do you think which words or which parts of the text you believe this is polite text? And then we let them to annotate it. So people annotate it like, hey, understand, like, accept, may, nominate. These are words that I think this is polite. Okay, that makes sense, right? And then we did the same thing to the model. And here we used one of the state-of-the-art classification model, which is called BERT. And then BERT, this model thinks, hey, these are important words that I think this is polite. And can you see the huge discrepancy between humans' perception about the politeness and model's perception about the politeness? Can you see? The only one word, accept, is the both human and machine think they are this is an important word as a politeness. Interesting, right? And of course, we use the state-of-the-art technique for everything, like getting this word important scores from the model, or getting the style classification from the model as well. So we thought this is quite interesting. So we decided to scale up. So we actually collect the data sets, and then we ask human annotators to see like which part of the text is polite or not. And also we take the best model, and then we ask which part is regarded as important words by the model. And then we do this for different styles, not just the politeness, but also sentiments, offense, and 5 different categories of emotions as well. And then we named this data set as hummingbird, okay? And then here's what we got. So we first look at what are the top words chosen by human or the model as important words for detecting this sentence is joyful emotion. And then both human and machine think excited, love, entertaining. These are important words. And human think moved, share, performances are important words as a joy classification. But the model think movies, managing, referring, these are important words. And I have a bunch of tables, of course, the other styles as well, but I will skip it. But look at the word movies. Why do you think model think this is important words to think this is joyful text? Can you guess? This is because this joyful emotion data sets, they are collected from movie review data set. And then by chance, this joyful label co-occurs with the term movies a lot. And the model think, hey, movies must be some important feature to detect joy. So this is data set bias. So model is basically learning this kind of data set bias, but annotating or making the model to learn the human's perception on the words like this, we can actually mitigate this bias. So this is the motivation of why we collected this lexicon level or word level importance. Okay, so and then why we do this? So we collected the data set across multiple styles, right? Not only politeness, and then we just project those words into this two-dimensional space, and then each word consists of how many? Like eight kinds of vectors, eight length of vector. And then each vector, we have the scores of like politeness, positive, offense, and so on. So maybe the word please is has 57% of politeness, 3% of positive sentiments, 7% of offense, and so on. And then you can see some styles are, and then the words that are meaning the similar stylistic meaning are clustered all together. And the funny, interesting thing is, you can see in the left top, all the words with the blue color, they're clustered, and they're basically content words, not about the stylistic words. And then you can see they're quite well disentangled with the stylistic words. But if you take the bird's representation or other embedding, semantic embeddings, they're totally mixed up. So there's no way to distinguish them. And then another interesting thing is, if you look at the left bottom, you can see that some positive style clusters are grouped together, like a joy, politeness, positive sentiments. And in the middle, it's more likely emotional. And then on the right side, it's going to be like more negative sentiments or offense, impoliteness, and anger. So in this stylistic embedding space, we can see that stylistic meaning is actually projected well across the multiple styles. So that's it about this work. And then the next step is, can you actually inform the model to follow this human's perception? And then this is what we did and then what we submitted the next paper to other conference. So basically, we take this hummingbird data set and then let the bird to mimic humans' perception. So which means, and then we name this kind of this system as StyleX. And then this system can do style classification as well as interpretation as well. So basically say, hey, I feel good is a positive style. It is sad is negative style, but good is the words that I think it's important to believe this is positive. Sad is the important word that I believe this is negative sentiments. And by doing this, we can actually increase this explainability or interpretability of this black box model. And also we can generalize well because the data sets, the test set of the benchmark data set, they're collected on certain domains. So if you deploy it to the other domains of the data set, they're not well generalized. But if you know which parts of the words are important, it's easy to generalize well, and no matter what domains of the data set is. So I will give you some example. And this is how the model works. And this is just a typical binary classification of whether this input sentence is positive or negative, right? But in the middle, we just plug in this word level predictor, and then we just make this intermediate layer to mimic the human's perception that we got from the hummingbird data set. So I will skip the details about the model. And then if you look at the actual output from the system, the first one is our system. The second, this robot thing, is one of the state-of-the-art interpretability methods. And then you can see that both systems think this is positive sentiments, but the second system thinks you can see that the things were very indeed. These are basically random, and you can see so much bias are learned throughout the training. But our system only detects the correct word, important words, to make this sentence to be predicted as a positive sentiment. And same for the negative. You can see that this mediocre and with funny, these are the important words to think this is negative. And by the way, this sharp means in NLP, we use the different tokenization methods, because even though there's a single word, each part of the word or each subtoken of the word has a different meaning. So we actually have some, we tokenize the single word into multiple pieces. So you can see this sharp is linked with the previous token. So mediocre is basically one word, but it's split it to 3 different words like this. Anyway, and then so this is some example from our system. And then I mentioned about the generalizability, right? So this works, so by adding the stylistic layer in the middle, it doesn't hurt the performance. But when you apply it to the other out of distribution data sets, we could also achieve some consistent improvements on the out of distribution data set as well. Okay, so that's the first part of the human-centric NLP. And I'm gonna take some questions first. Nathan, so do you account for the context of a sentence since the same word could be important in one sentence? Yeah, that's really good question. And this BERT model or many other state-of-the-art models, they're supposed to understand the context. So the meaning of maybe like the word please might be different in other sentences, right? Or in across the sentences, right? So they have a different semantic representation of this word please according to the text. So this is how this contextualized model works. But in our setting, we also, in our annotation over these words, we also have this variation of the stylistic meaning. Although we only show the top words, but that's this aggregated score. So they are the top words in the table that I showed. They're just generally important words, but each word has a different variation of this importance across the sentences. Yes. So that's why we collect the annotation per sentence. Yeah. And then traditionally people think, hey, word is same for every sentence. So they make some dictionary, lexical dictionary for positive sentiments and negative sentiments. But as you said, it doesn't work across the different contexts. So that's the traditional approach. But nowadays, people try to reflect more context information. Yeah. Any other question? Or... Okay, then probably I will go into the next part. What time is it? 3:09. Yeah, maybe I have to skip the second part, data-centric part. So I will only focus on the interactive NLP system part. So second part is about how we can make the systems to be more interactive with the real users. So I call it interactive NLP system. And then let me just move into, and then I focus on specific domain, which is basically scientific domain. So this system is basically built to help scientists or academic researchers or anyone who involves in the research community. So but our basic goal is, can you help them using some NLP technologies? And then how can we help researchers in the scientific community? And then what are their activities in the scientific domain. So people in science, they read papers, they write papers, and sometimes they review someone else's paper, right? And then for reading, think about like how we can help people's reading experience. So the system may help like different types of style reading experience, right? Some people may skimming, some people may do some proofreading, or some people may have a close reading, which is basically trying to like deeply understand all the details of the paper or manuscript, whatever. So this is called the close reading. And then what about the writing? So maybe the system can automatically suggest what possible texts or mathematical notations to type in. Or the system can detect, hey, this part and this part is inconsistent in your writing. Why don't you make them consistent? Or the system can automatically revise some parts if they think this is not clear, this is not fluent, and so on. Or when you're reviewing someone else's paper, a system can help reviewers' judgment by providing some automatic judgment scores. Or we can help, the system can help verify that, oh, this main claims of the paper is not that good, or it doesn't make sense at all, something like so. And then there are existing systems that are actually helping over those aspects. And these kind of practical NLP systems can contribute to improve the science community, of course. But at the same time, we as an NLP researcher, we can also learn a lot from this kind of interdisciplinary collaboration, because there are many interesting NLP problems happen while we are working on this. So it's a good synergy. Yeah. And today I'm going to describe about two things. One is about close reading, and the other one is what we are actually co-writing the grant proposal regarding this writing assistant. So about the close reading, here is an example of the close reading. So, and then how our system can help. So if you read a paper, with a lot of mathematical notations, or a lot of like heavy math or machine learning, deep learning, physics papers, you may often see that many different terminologies are defined here and there. And these new defined terms are called basically nonce words. And in fact, each paper has a lot of nonce words. And these nonce words can be like words like acronyms or symbols, mathematical symbols, or new terms. But the thing is, when you read the paper, you have to memorize all these newly defined terms and then put them on your memory, right? It's really painful, and it requires a lot of like cognitive load. So we developed an augmented reading interface that can actually provide just-in-time and position-sensitive definitions of these nonce words, which is called Scholarify. So how it works? So if you read a paper using our PDF reader, and if you click a term, acronym, or symbol, the system shows its definition defined within this paper. So this is an example. If you click this H, subscript H, then system automatically finds where H is defined, and then store them, and then show its definition in this tooltip bar. If you read a paper, and then if you see like this complicated equation, and if you click that equation, you can see this sort of like equation diagram. So better understanding this equation diagram without going back and forth across the pages. And also, if the reader likes to print it out and then read maybe at home, then the system produced extra page of summarizing all the terms and symbols defined in the paper with their definitions detected. So this is called this Scholarify system we built. It will be like a default PDF reader for the AI2's Semantic Scholar. Semantic Scholar is a kind of like Google Scholar developed by AI2. So this will be the main default PDF reader of that system. And then you can use it pretty soon. Yeah. Okay, now let's jump into the writing parts. So how can we improve researchers' writing experience? So for instance, when you write a paper using LaTeX editing tool like overleaf, the system may help you by flagging some error messages of inconsistently used terms, and then suggesting possible revisions. Hey, this part is inconsistent. Why don't you change like this way? Or the system can show that, hey, this paragraph you just wrote, it's not clear. My coherence score is 0.6. Why don't you revise this way? So the system also can suggest some revised text. Also, system can automatically suggest what symbols or terms to type in for the next couple of words by understanding the whole context of what you have written so far. So these are how NLP systems can help and then improve your writing experience. And then we are currently writing a grant proposal, and then we are collaborating with Grammarly, which is another writing assistant company. So I hope like we can actually transform, my long-term vision is transform our writing experience to interactions with the AI systems or NLP systems. And then, yeah, of course, we are working on some co-organizing some joint workshop between industries who are working on this writing assistance and academic researchers who are working on this writing or NLG or other automatic NLP systems. Okay, so that's all about this interactive parts. But I think I only have 14 minutes. So I will only cover the first part of the data-centric NLP. But before jumping into there, any question? Okay, then let me move it. So in the second part is totally different. It's not about the humans. Humans are not involved at all. So we only look into the data in the training data set, okay? And then we tackle the two things. One is data augmentation. The other one is data annotation. But the basic theme that I have is, hey, we better focus on, can you measure the informativeness or value of your data points? And then making some smart way of choosing the data sets to annotate or augment. So that's the basic thing. I will give you the details in the following slides. So let's go back to this NLP pipeline, okay? And then, as I said, my basic theme is, hey, we bring the machine for data annotation parts. It's not just the human annotators make some data collection, but we also bring machines in it. And then let machine and annotators collaboratively annotate or collect high quality data sets. So that's the main thing. Then how can we find those informative data points in this collaboration between human and machine? How can we diversify the data points so we can avoid the repetition or artifacts in the annotation process? How do we measure the value of your data points? What aspects do we need to consider? So these are all like open questions, and these are like all the questions our group is actually working on heavily these days. So one work is about data augmentation. As I said, data augmentation is basically augmenting or bootstrapping your data set. So there's no additional human involvement or human annotation, but just take the annotated data set and augmenting more and more and more again. And they're slightly different, but if you train your system with augmented data set, your system might be more robust because you have a lot of other data sets, right? So that's the basic concept. I will give an example. So it's basically given data point X, you augment new data points X hat. How? So X is like a sentence like, it is awesome. And then by using some tool, I will get into that there yet, but there's some tool, and then you got the new data point, which is, it is amazing, but they're meaning the same still. So the label is the same. Maybe label for this one might be maybe a sentiment for sentiment task, sentiment classification task. The label is both like positive sentiments, right? How? because linguists developed a lot of like this lexicon dictionary called WordNet. So we know that awesome, amazing, good are all like a synonyms. So it's still safe if you replace awesome with amazing, and then there's no meaning change at all. So this is one technique. And in fact, over the last few years, people developed a lot of different data augmentation techniques. And then why? Because it's useful. And many companies like Google, Facebook, they all use this augmentation technique because they are guaranteed to get some extra improvement of your system for machine translation, summarization, whatever. Okay, then here comes the problem. If you apply these different augmentation techniques to different NLP tasks, their relative improvements are so much random. So it's not guaranteed that this specific technique, like technique called EDA, technique called adversarial, technique called word augmentation, cutoff, whatever, it's not guaranteed that they are always like consistently making good progress across the tasks, NLP tasks. So it's so much random, and then nobody knows what's happening inside. So I will give you a question then. What makes good augmentation? And then is it possible to find or develop a system that can find the optimal combination of these different augmentation techniques and then make some consistent improvements over different tasks? Is it possible? So that's the question we like to solve. And then in fact, we did some simple study. So here is, so we project each data point into this two dimensions. So y-axis is, there's already like a pre-trained system. And then we feed the sample to this system and then see that whether the model is confident in making the prediction. So 1.0 means, hey, it's too easy example. I'm super clear. But 0.2 or 0.1 confidence means, I'm not certain about it, something like that, okay? And then what x-axis is similarity between original x and then augmented sample x hat. So having 1.0 similarity means x and x hat is almost identical, which means basically no meaning as an augmentation, right? But if they're too different, maybe the labels might be flipped. So we lose the semantic meaning constraints, right? So what we did is we take each augmentation technique and then project the data points using each augmentation technique, and then it comes out. So you don't need to know about like which technique is what and so on, but just look at their distribution. So one technique called adversarial methods, they always like biased to augments very similar augmented samples to the original samples. If you look at this white hexagon samples, they're biased to produce always very confident samples. Then I'm going to give you questions. Which parts of this area is the golden spot as a good augmentation? Can you guess? We don't have time, so I'm going to give you an answer. So this spot is maybe probably the answer. Why? Because we need some difficult examples, which means less confident by the model, but at the same time, we shouldn't lose the original meaning. So the augmented sample should be quite similar to the original. So having this augmented sample to be difficult, but not too different with the original sample. That's our philosophy or assumption, okay? And then based on that, and here's an example of what we augmented from our system, but we don't have time. But if you control this, P is here is a confidence, S is a similarity with the original sentence, but you can see the different variation of augmented samples by changing this scores, but I will skip it for now. And then, yeah, we control this difficulty and the similarity using some reinforcement learning model, but I will skip also this. And then we got the consistent improvements over different tasks, and then we almost like a bit most of the existing augmentation method using this, but I will skip. And then, as I said, for each task, NLP task, we find the optimal combination of this different various augmentation techniques like this. Yeah, let me just skip it. Okay, so that's about like we make an assumption of good data augmentation might be having similar but difficult samples, right? So that's our assumption. Then let's go deeper into that assumption a little bit more. So here's another projection. This is done by someone else, not me, but I think this is cool, so I just brought it. So now y-axis is still the same, confidence, okay? But now x-axis is different, so it's called variability. So how we measure this? So this is basically neural machine learning system. So you may have a prediction of each data point over the course of the training. So you can get the prediction score y at the epoch 1, epoch 2, epoch 3, and so on. And then can you guess? And then we measure. They measure this variation of this y over the epochs, and then it turns out the projection look like this. So high confidence but less variable over the training. These are easy to learn samples, but intermediate confidence but high varying. It's making prediction like, hey, this is positive, but this is negative, positive. It's fluctuating, then it's really ambiguous, right? But less confidence, but less variability. So model is not changing the prediction at all throughout the learning, but it still has a low confidence. It's hard to learn. So this gives some information about like which data point is informative or valuable, right? And then motivated by this work, we actually think each data point has a different importance. And then we actually look into various kinds of the sort of like the training dynamics or informative scores using different measures. And then we make this informative representation. And then this is different from your semantic representation. Semantic representation, this is intent task. And you can see that there's a clear cluster between contradiction samples, neutral samples, and intent samples. But in this informative sample, you can see that quite interesting clusters exist across the semantic space. I will not go into details, but using this informative space, what we're trying to do is, given a new input data, we measure whether the valuation of this data point is 0.68. So this is so much important. So you have to annotate it. So this is the idea, picture of what I'm saying, like data-centric data annotation. Okay, so that's all about my talk today. Yeah, sorry to rush at the end of the talk, but yeah, thank you for listening my talk. And I think there's one question. Rahul, how are long time or ternary dependencies handled in such systems in case of long paragraphs? Traditional writing assistant do not work well on such long time relationship. Is there any way? Okay. So are you talking about this latency issue, like making predictions in short time, but when it goes to the long documents, the prediction might be really slow or something? Yes, this is really good question. And when we are working with Grammarly, to be honest, I don't take care of this issue because there are many dozens of engineers at Grammarly who are working on this efficient inference module of this transformers or BERTs. So that's their part, yeah. But I will give you some pointers. So there are existing or ongoing work on making this huge BERT or GPT-3 models to be efficient. Efficiency here means that having less parameter, but having the same, but guarantees to have the same performance. So this efficient model or long former or these kind of linear former, these kind of models are all about making having the fast inference time prediction. So you can take a look at that. Yeah. But that's not my area though. Any other question?
I have a question.
Mhm.
First, very interesting talk. I thought it was very approachable. I was wondering, so one of the things that often comes up as a Spanish native speaker is that, for instance, my parents won't be able to pick up that you might encounter because words are used, more than one way. So for instance, you have the LOL, right? That's been a meme on the internet where some people thought it meant lots of love, but most young people use it as laugh out loud. Where do you see the role, or where do you see systems like yours going in the future towards helping or assisting people understand the context of slang in language?
Okay, that's a good question. So there are a bunch of work in NLP who are working on the slangs or new words or evolution of the words. And yeah, some words just disappear, some words just pops up from internet usage, whatever. And then this kind of like big models, they just use the snapshot of languages written by multiple people, but they don't handle this dynamics of the language. So what I like to say is these models are not able to handle this dynamics of or evolution of the languages, but there are some analysis about how language evolves and new words can be handled by adding some temporal dynamics over these models and embedding spaces and so on. So I can give you lots of the pointers to them, but to be honest, it's not an easy question when it comes to this big models. Yes. Does that answer your question?
Yeah, definitely. Thank you.
Yeah. Any other question? Or if you have any question, just feel free to shoot me an email, or we can also chat in offline if you want.